Hello everyone, my name is Liam. I'm a math and computer science major here, and I'm presenting Lookahead branching heuristics for neural network verification, which is my ongoing project I plan to submit to NeurIPS in less than a month. And we'll get into all of that means right now, but first I'll start by posing a question. Can we trust neural networks in safety critical domains? And what that means is if ChatGPT hallucinates and gives a bad response, it's not really a big deal. But if we're implementing neural networks everywhere, they're going to be implemented in places where people could potentially die if they make mistakes. So in these applications, it is very important that you have absolute certainty that they perform across every possible inputs, which is a big reason why there's a lot of hesitation in implementing new AI systems in these such applications like autonomous driving or medical equipment. And if you don't believe me about how this could be an issue, this is from the last Mark Rober video. He pulled the Wile E. Coyote trick on Tesla autopilot, and I don't know about you, but I don't want my autopilot to randomly drive off a cliff or something. So this is where neural network verification gets in. So first, what is neural network verification? So neural network verification is a process in which you prove a certain property about a neural network across every possible input with mathematical rigor. So you get a formal guarantee about its behavior. So this is kind of the schematic for it. So you have a neural network which at the low level is a function, and you have a property you want to prove. You feed it through a verifier, and you either get that the property satisfies or the property is unsatisfiable. So one such property could be like a reachability property, where you say, okay, I have this malicious output that I don't want the neural network to ever be able to produce. How do I prove that it will never reach that output? Or another one, a more common one, would be a robustness property, which says if we add adversarial noise to the input, we don't want the output to change, or in a continuous case, the output to change a significant amount. But there's one problem. Neural network verification is slow, and this is because that to prove something over all possible inputs, you have to do exhaustive search over the input space, and neural networks, especially in practical applications, are very large, so it is definitely a very slow process, which is where my work comes in. So here's a little preliminary on how neural network verification actually works, so you can understand my work. So it's focusing on ReLU splitting, which a ReLU is an activation function that returns the max of 0 and the input, so you could think of it as having an active or inactive state. So what you could do is you could basically split on a ReLU and turn a big neural network verification problem into two, one where it's in the active state and one where it's in the inactive state, and propagate the bounds for the possible outputs like that. So in this sort of search tree over here demonstrating it, at the root you have one ReLU, you split it into the active and inactive state, then split on another ReLU, and then you propagate the bounds. And when a ReLU becomes phase fixed is when it can either only be in the active or inactive state, so that would mean the output can only possibly be positive or negative. So that is a little bit on ReLU splitting, and now we get into Lookahead branching. So obviously when you're doing this ReLU splitting, the choice of ReLU that you branch on is very important because it determines how big the search tree underneath that ReLU is going to be and how quickly you converge to SAT or unsat. So it is a very critical problem to find the best possible ReLU to split on. The problem is that the standard heuristics that have been developed so far rely only on local information like the bounds of a ReLU currently, or the instability or something. But what I did is that I implemented an online learning approach taking from SAT solving literature using a Lookahead approach, where at certain critical branches you are going to simulate a bunch of different splits on different ReLUs, and then you are going to simulate the downstream effect and then choose the best ReLU. So obviously you're adding overhead there, but when you do it in the most critical branches, you're making sure that those branches are as good as possible. So the first thing you have to do is, obviously, if you simulate splits on every single row in the network, networks have thousands, hundreds of thousands, sometimes even more neurons, so that is very inefficient. We have to have a pre-selection process. So the first thing we're doing is that we're going through each row and we're giving it a score using the upper bound and lower bound. And this tries to predict or tries to eliminate the rows that you don't have to do look ahead on to see if it's going to be an effective split. You know it's already not going to be an effective split. So we choose the top K candidates for rows with this high score, and then we do look ahead on this. And when I implemented this in Maribel, K was 20. When I'm implementing it in Alpha Beta Crown, it might be different. It's a tunable parameter. And now we go into the look ahead strategy. So this comes directly from SAT solving literature. So for each pre-selected row, you're going to simulate branching on both the inactive and active state. So basically, you're just going to build a mini search tree, and then you're going to use a standard heuristic to choose another row and do the same thing. So you have four different branch or leaves at the end of this, and you're going to, and in each of those four leaves, you're going to count the number of phase fixes, or how many new rows were phase fixed as a result of this branching and bound propagation. And then we're going to calculate a score for each root neuron. And the score is, if A and B are the phase fixes on each respective side, it's going to be 8 times B over A plus B. And the intuition behind this is that you want the max number of phase fixes possible, but you want balance too. So in this case, let's say one side's 9 and the other side's 1, versus if one side's 5 and the other side's 5, this will score the one where it's 5 and 5 higher, because you do want balance there. And then obviously there are 4 leaves. You propagate the scores up to the parent nodes, and you use that to then as the values for A and B for the score for the root node. And this is also a tunable parameter for how deep you go. 2 was where kind of the convergence point for Maribel, but obviously it's a tunable parameter, could change for other implementations. And once we do this look ahead strategy, we're going to then just reset the state, because if you don't reset the engine state, or it's you could get to some infeasible states. So that's a problem. So you just want to avoid that, and then you're going to branch on the row that got the highest score. So this ensures that at this branch we're doing the as best of a possible of a split, and we're doing this at critical splits. So in my Maribel implementation, I did it on the first 5 splits. I also experimented it on doing every 10 splits or so, but that did not perform as well. But obviously there are multiple ways to do it. So, and here are some of the results. So I tested it with 3 different heuristics, comparing it to the baseline. So BABSR, which looks at the upper and lower bounds and tries to predict which ReLU will make the biggest impact. Polarity, which focuses on ReLUs close to 0, and pseudo impact, which does stuff with the sum of infeasibilities. This is a Maribel specific approach. So as you can see over here with the comparison plots, the diagonal lines that equal comparison, so everything below the line will mean the look ahead is better. Specifically on unsat instances, there is significant improvement here, and a lot of unique solutions, especially with polarity and BABSR. You might say it does not perform as well on SAT instances, which is correct, except with SAT instances, the best algorithm for that is usually an adversarial attack algorithm, where you start with an assignment you think will satisfy and then just iteratively update it. So we're less concerned about SAT instances here. And one thing I'm actually experimenting in Beta Crown 2, because it do a lot of parallelization there, is actually running an attack algorithm and look-ahead branching in parallel. So the idea is that you optimize for both stat and unstat instances there. And then we'll go into some cactus plots here. So on the left is for the stat instances, you see that we are adding some overhead that is definitely seen in the stat instances, but like I said before, that is less of a concern. But on the unstat instances, we could see that it's about when the runtime exceeds 1 second, that's kind of the inflection point where the overhead associated with lookahead starts to be less than what you gain from having better branches. So especially as complexity scales up, the look-ahead branching does get better there. And with that, I'll go into a little bit of future work now. Right now, in preparation for NeurIPS, I implemented all these results are from Marable, which is one framework, and I'm currently working with the Alpha Beta Crown team, which is another verification framework to implement it in there and then yield the results so I could have stronger results, and obviously, like I said before, running an attack algorithm and look-ahead branching in parallel. But some avenues of future work too are input splitting with look-ahead. So in verification, instead of starting directly with the ReLU splitting, I start with splitting the input into a bunch of subproblems so they're more manageable. So doing some look-ahead on that could be useful. Also, just improving the branching heuristics in general, because the current branching heuristics, I won't sugarcoat it, they just kind of suck right now. So just finding ways to improve those could also be very helpful. And also alternative online learning strategies. I took Lookahead directly out of the SAT literature, but I was also initially exploring some multi-armed bandit framework where you treat each ReLU as a bandit. And I ended up not opting for that based on some experimental results I got very early on, but it could be something that definitely could yield some results too. And with that, I would like to thank my professors that I've been working with for their guidance and support. Professor Lua has been with me every step of the way on this and has been a lot of help. Professor Clark Bear over at Stanford, he runs the Marable team, and he's been helping me out for the last few months too, and definitely offering a lot of support. And Professor Juan Zhang, who's at UIUC, he runs the Alpha Beta Crown team, and he's the guy that I've only recently started to work with, but it's been a lot of fun working with him so far. And I'd also like to thank everyone else that's on the Marable and Alpha Beta Crown teams. So both of these frameworks are done with teams that are multi-institutional and multinational. So there are a lot of people on this and a lot of people that have given me advice and support on this. So I can't list them all here, but I would also like to thank them. And with that, thank you for listening. I've attached the GitHubs of both of the frameworks I'm implementing this in. I would say that the two frameworks at the last verification of neural networks competition placed third and first respectively, and are the two best open source frameworks out there. And with that, I'd like to thank you for listening, and I'm open to questions.
Take just one question here.
Yes?
When it doesn't go right, how bad is it?
When it doesn't go right, it is pretty bad. So which is something you see in verification, where one heuristic is really good in some instances but really poor in other instances, and that's just something you can't really get out of the way of. So the way you counteract this is obviously by running different strategies in parallel, or also both frameworks implement restart strategies where if you detect that it is going bad or not going anywhere, you just cut it, restart with a different strategy, and try to solve the same problem.
I think for the sake of time, else have any